Now that we understand the definition of cylindrical coordinates, we're going to want to use these to help us compute integrals over regions that are better suited to be thought of as portions of cylinders as opposed to portions of rectangles or boxes. And so for that we're going to have to compute the Jacobian of the transformation. I wrote down in the end of the last video the transformation itself. I'll rewrite it here. So the transformation, and remember the cylindrical coordinates are just polar coordinates in the xy plane and leave z alone. So the transformation is pretty nice. It's not too new for us. We can think of it as a nice separation of the xy plane from the z-axis. So the transformation is x equals r cosine theta, y is equal to r times sine of theta, and z is itself just z. And remember, the idea here is that we think of cylindrical coordinates, they get their name from the geometry here. We think of cylindrical coordinates as being a bunch of cylinders centered around the z-axis. So the z-axis is the height in the usual sense, but then we think of the x and the y coordinates just being polar down below here. And so any point, say this point sits at a height z, okay, and then it's got polar coordinates in the base, polar coordinates that come with a length and an angle down here. And so this is all cylindrical coordinates are. It's just polar coordinates in the base stretched out vertically in the z direction as a, the same as a rectangle would be. Okay? Again, if we're going to use these coordinates to help us compute integrals, then we absolutely need to know the Jacobian and the volume element. So the big question here is, what's the volume of a small, tiny, infinitesimal piece of this cylindrical shape, right? And so it turns out that a cylindrical volume element gets its shape from, because these coordinates are built by circles in the base, so polar coordinates downstairs, and then just a vertical height. You might remember that a polar rectangle looks like a wedge, so it's a sector of a circular region, a sector region that's been chopped off. Okay, and so this is like a tiny piece of area in the xy plane, and the idea here is that we've got some change in r, and we've got some change in theta. And remember that the change in area of this piece, so red and blue make magenta today, so the change in area of this piece, we worked this out in the polar coordinates section of the notes. The change in area, you need a test point, usually it's the midpoint right here, and you end up with r star. I'm not labeling the I, J, it's not a big deal here because we've already worked this out. Okay, but this you get an extra factor of this r star, and what this leaves us with is that dA, the change in area, is r dr d theta. And this is just review of polar coordinates. So if this isn't familiar, go back and brush up on your polar coordinate transformation for two-dimensional regions. Now, once we're in 3 dimensions, the third dimension here is just z. So the height here is just going to extend our wedge and give it some volume now. Okay, so this portion here, this is a cylindrical volume element right here, or a tiny piece of volume in the cylindrical sense. And we need to know the volume of this thing. But for any shape that we can understand this way, that's just built by taking parallel slices in some sense, the volume is just the area of the base times the height. And the height of this thing, this tiny little piece, this height is just a tiny, tiny change in z, delta z. Okay, and so our volume element is going to be, our delta v should be the height times the change in area of the base. So tiny height times the tiny change in the area of the base, and as we computed, or as we remembered, the area of the base is given by this formula. So the cylindrical volume element should be, dV, and it is, of course, should be dz times this. I'm going to just rearrange it and write it as r dr d theta and then dz. Okay, so this is a geometric argument, remembering all the work that we did in polar coordinates, and then just saying that, okay, in the third dimension, this is just extending up the height here and making a little box, in some sense, a polar box out of this shape. All right, but we have already studied the Jacobians of transformations in this class, so we should be able to check this and hopefully get the same formula, but we should be able to check this by computing the Jacobian of this transformation here. And so let's do it. I think I can fit this all on this page here. So remember that the volume of a small rectangular prism, our dv in rectangular coordinates, is just the product dx, dy, dz. And so we need to compute the Jacobian of this transformation to see how the volume changes when we switch coordinate systems. So remember how the Jacobian works. The Jacobian matrix, J with a hat as I call it, this is going to be a function of r, theta, and z. It's a matrix whose components are the partial derivatives of these transformations. So I'm going to write it in symbols. It's dx, dr, dy, dr, dz by dr. That's the first column. You take all the r derivatives of these functions, and then you go to the theta derivatives. Dx d theta, dy d theta, dz d theta. And then you go to the z derivatives. So dx dz, dy dz, and then dz dz. And of course we need to fill these in with functions. And so we just compute the derivatives. So dx dr is just cosine of theta. Dy dr is just sine of theta. And dz dr, that's 0. There's no r's in this equation. It's just z is just equal to z. And now we go through the theta derivatives the same way. So the theta derivatives are going to be negative r sine of theta. That's the theta derivative of x. Then it's going to be r cosine of theta. And then again 0, because z doesn't have any thetas in its definition either. And finally, the third column here is the z derivatives of these functions. And now the roles are flipped, right? So x and y do not depend on z. There's no z's in their equation. And z only depends on z. And we can easily compute that these derivatives are 0, 0, and 1. And so that's our Jacobian matrix. The next step, though, this is not the Jacobian that we need for integration. So the next step is to take this matrix and compute its determinant. And that's the Jacobian determinant, Jacobian function, the Jacobian that we need for our transformation in terms of the integration. So I'm going to go to a new page and remind ourselves that this is our Jacobian matrix, which I've always called J with a hat. And our Jacobian determinant then is literally the determinant of this, our Jacobian function. So this is what we need to multiply by our area element, volume element in this case. So this is a 3 by 3 matrix now, so the determinant becomes a little more complicated in some sense. There are a couple ways to compute a 3 by 3 determinant. There's a definition, which if you've taken linear algebra, then you know you have to systematically build these things called adjoint matrices and take smaller determinants, etc. But there is a kind of a trick, I guess, that you can use for a 3 by 3, which, since we're just computing these things in general, I'm happy to share with you. Whenever you use some kind of, I call this a trick, maybe that's not the best choice of words, but whenever you use some kind of method, you have to make sure you understand why it works. So I'm just going to give you the method, and then you should go review determinants if you need to. But the method here is to copy the columns, the first two columns, and copy them over on the other side of the matrix here. So outside of here, I just copy the same columns, just the first two though. So minus r sine theta, r cosine of theta, and then 0. And so now I have a system where I can multiply these main diagonals and also multiply these off diagonals. All right, there's a lot of zeros in this one, so anything that has a 0, I'm going to multiply these together individually and then add up the red and subtract off the blue. Okay, so the determinant of this is going to be the product, so it's going to be cosine times r cosine times 1. So that's r times cosine squared theta, plus 0 plus 0. These two diagonals here each have at least one 0. So plus 0, minus the sum of the blue one. So this sum right here, this product is 0. This product is 0. This product, though, is minus r sine squared. All right, and so if you follow this process again, the red ones get added, plus, plus, plus. The blue diagonals get subtracted. And as long as you're careful, this method will always work for a 3 by 3. What we're left with here is that we end up with r cosine squared theta plus r sine squared theta. Of course, we can factor out an r. And then we see a Pythagorean identity here. Cosine squared plus sine squared is just 1. And so this computation shows that the Jacobian of our cylindrical transformation is just a factor of r. Well, what does that mean? Remember how the Jacobian helps us with integration? Our volume element, dv, in cylindrical coordinates is dx, dy, dz. Again, you can change the order here. This is in Cartesian coordinates. I think I may have misspoken there. But this is the Cartesian volume element. And according to our study of transformations, the volume element in cylindrical coordinates has to be always the Jacobian of our transformation times the dv in the polar coordinates. So let me just write this a little more clear here. So it's this Jacobian times dr d theta dz, and if we've computed here that our Jacobian is just r, then that's the factor that we have to multiply this by. So dv in cylindrical coordinates is r, dr d theta dz, and this matches exactly with the geometric justification that we gave at the beginning of this video lecture. Cylindrical, this is our cylindrical volume element, and this is what we need to multiply, this is what we need to use when we do any integrals in cylindrical coordinates.